So today we're going to be talking about graphing logarithmic functions. So I want to talk about what a log is and what the reason for a log is. So if I said to you, you don't have to write this down, just pay attention to it. 2 to the x power is equal to 8. What would you tell me x is? 3. And you did that by just kind of using guess and check, right? We kind of know that 2 times 2 times 2 is 8. But what if I said to you, 2 to the x power is equal to 13.75? Would you be able to tell me that?
No, probably
No,
not.
and we haven't learned any tools in this class that would allow you to solve for that missing x, right? You see this equation, is there anything you know how to do to solve for x? No, because we haven't learned how to deal with when we have an unknown as an exponent. So today we're going to learn about logarithms, which is a solution to that problem. So you're adding a skill to your math toolbox with logarithms, okay? And that allows you to solve for missing exponents. So let's go ahead and get into the logistics of it. So every exponential equation can be rewritten in logarithmic form, where log, right here, the subscript is the base. Okay, so like if you have 4 to the third power, that's the base of the 4. X is the answer and y is the power. Okay, so if we have it in this format, we can convert it to logarithmic format. There are restrictions, and those restrictions are based on the same restrictions that happen with exponents. Is there ever a situation where you can put a number to an exponent and it comes out to be a negative answer? No. What about if you have something to an exponent, will it ever come out to be 0? Is anything to some power equal to 0? No. And lastly, what is anything to the 0 power? 1. So that's where the restrictions come in. So let's go ahead and try to write some conversions. So how do you go back and forth from form to form? Well, if you're going from log to exponent, it's pretty easy. We use the arrow rule, okay? So that's going to be 4 to the second power is equal to 16. Okay, that's how you go from log to exponential. Okay? Everybody getting their notes down? Paying attention? Okay. Next one. 3 to the 6th power is equal to 729. Okay. So that's how you go from one form to the other. Now, we're going to try going the other way around. All right, so now that you've seen a few examples, this is going to be log of what? Base what? 4 of
64.
Good is equal to 3. So you say you can transfer back from one form to the other. Now, you're not doing anything right now. We're just learning how to transform. Okay, this is a tool for solving, but first you have to understand how they go from one to the next. And then lastly, we have log base 125 of 5 is equal to 1/3. So everybody at least have an understanding of how we go from one to the other now. Okay. So now we're going to use that skill to find missing values. Okay. First thing you have to do is you're going to set your logarithmic expression equal to y. You could use another variable if you want to, but we're going to use y. You're going to rewrite via definition of logarithm. That's what we just did on the last page. And then you're going to change it to a like base. So if you're wondering where we learned about this was 7.3. And if you want to put a note there, if you're on a test or a quiz and you want to be like, wait, where did we learn this? That was in 7.3 where we learned that. So from here, from the steps from here to here, that's all 7.3. So we're kind of like using those skills in that step. And then lastly, if there is no base on your logarithm, you assume the base of 10. Okay. So if you ever need to know that, it's here on your notes. All right, let's go ahead and try number 5. First thing you're going to do is you're going to set it equal to y. So whatever the variable is, you want the variable to be on the right side, backwards from how we usually do it. And now we're going to use our arrow rule. 3 to the y power is equal to what?
81.
81. So we can use rewriting to help us solve this. So I'm going to keep 3 as 3 to the y. Now, is there a way I can write 81 so it's 3 to some power? What do you think? You got an idea?
3 to the third power?
3 to the third would be 27.
Oh, 3 to the fourth.
3 to the fourth, right? Everybody see what I did there? Rewrite it as an equivalent expression. So what you then do is you set the exponents equal to each other, and we get y equals 4, right? Would you all agree with that? Because if you do 3 to the fourth power, it's 81. Now, we're going to learn about this calculator step in more depth in the future, but I just want to show you it so you can start using it to check your work. So there's a thing called change of base formula with a log. If you have a log of a base and of something, you can do log of your number over a log of your base in the calculator, and that will actually give you your answer as well. So this is a way to check your work, but like I said, this is not going to be an end-all be-all. I just want to show you it for today. So I'm going to show you how to type this in. So in your calculator, you're going to type in 81, you hit the log button, divided by parenthesis 3 log, close the parenthesis, equals. What did you get?
4.
4. Look at that. See how you can get the answer using the calculator too. And the reason for that is not all of these are going to be something nice. What if I said this was like 81.5? You wouldn't be able to do it so easily by using change of base, which is why we have the calculator as well. But before I get into anything with the calculator, I want you to understand why things work, not just how to do them. So now we're going to set this equal to y, and we're going to use the arrow rule. That's going to be 1/2 to the power of y is equal to 256. Now anytime you have 1 over a number, you can always bring that number up to the numerator by putting it to the -1 power, right? And now I can think of, there's possibly a way I can rewrite 2 to some power that would give me 256. Any ideas there? Well, 2 to the 6th power is 64. So 2 to the 7th power is 128. So if I multiply that by 2 to the 8th. Everybody with me on that? Now I can set my exponents equal to each other. What is -1 times y?
Negative y.
Negative y is equal to 8, which means that y is equal to -8. Okay?
How do you put this in your calculator?
I don't want you to worry about that too much right now. I can go through it again with you after in the notes if you want. But you don't need to for this lesson. I was just trying to show you like how it works a little bit. But if you're struggling with that one, just come up at the end and I'll show you.
Okay.
So this one here, we're going to set it equal to y. And then we're going to do our arrows. 9 to the y is equal to 1 over 81. Right? Now let's think about it for a second. Isn't 1 over 81 the same thing as 1 over 9 to the 2nd power? And how can I bring a number up to the numerator? I can do what to the exponent? Make it negative. So then I just set my exponents equal to each other and I get y equals -2. So something to think about. If this were just 9 to the y equals 81, you would know, oh, that's 2, right? 9 to the 2nd. If it's 1 over 81, -2. Okay, it just flips the sign of it. And then the last one we're going to talk about in this topic right here. What did we say the implied base is if we don't have one?
2.
No, it's 10 actually. It's over there on the notes.
Oh.
That's okay. Yeah, it's 10. interesting. And you can always remember, here's a little trick. You don't have to memorize stuff in my class too much because I give you open notes. But if you're on an SAT, say you forget, you blank, look at the button that says log on your calculator. You see the green, what does it say?
10x.
10x, that's the base. And then the base of ln, which we'll learn about eventually, is e. So it's on the calculator to help you remember. Little trick, in case you forget, it is on your calculator. So how would I go about setting this one up? 10 to the
Y.
is equal to
100.
100. This one you can probably do in your head. 10 to what power is 100?
Squared.
Yeah. So y is 2. And at the end, if you want to practice more with the calculator and you want some help, I'm happy to help. So let's go ahead and look at this real world problem. I'm going to try to read this the best I can. There's a lot of big words here. So, logarithmic modeling in a real world context. Photography. The amount of light in a photo is controlled by f-stops. The formula n equals log base 2 of 1 over p represents the proper f-stop setting n based on the amount of ambient sunlight p that is present. Benito's camera is set up to take pictures in direct sunlight. However, it is a cloudy day which allows only 1/4 of the amount of direct sunlight. How many f-stop settings should Benito adjust the camera to accommodate the reduced amount of sunlight? So that's a lot of words, okay? Now, first thing I always do when I see a word problem is if they give me a formula, I'm going to write that down. I know that's going to come into play, okay? And that's the formula I'm going to be working with. Now, usually the other thing you're going to start figuring out about doing word problems is there's going to be another piece of information that is going to plug into one of your two variables. You have to determine which variable that information is going to be plugged into. So you can see here they give us the 1/4, so we know that's going to be part of our problem. So let's read the context of that. However, it is a cloudy day which allows only 1/4 the amount of direct sunlight. That tells me right there. N is the number of f-stops. P represents the amount of sunlight. So what is my 1/4? Is it N or P?
P.
P. Okay. So I'm going to plug that in for P. Everybody see what I did there? Now, here's where people get tripped up for some reason. What is 1 divided by 1/4? If you don't know, you can do it in the calculator. What's the reciprocal of 1/4?
2.25.
It would be 1 divided by 0.25, which would be 4. So that's what I get. Now we have learned how to solve this. But to do that, I'm going to rewrite it like this. Why would I rewrite it like that? Any guesses? What can I do with it now that it's rewritten like this?
You can use the arrow method.
Very good. Can use the arrow method, right? So now it's going to be 2 to the n is equal to 4, which means n must be what? 2. Very good. So this is one of those scenarios. You see a problem like this on the SAT, and it's terrifying. It's a lot of words, a lot of big words. But it's really nothing very difficult of a problem once you know how to do it, right? No like difficult math or anything like that. Okay? All right. So moving on. Now we're going to get into graphing, your favorite. So I know a lot of you get very nervous about graphing because graphing can be scary. I always was anxious about graphing too, but we're going to take it slow. We're going to address all of it. I try to make it as easy as I can for you. I try all the different possible ways I can explain it and come up with the easiest one. So see how that goes. So let's talk about logarithmic graphs. We learned that logs reverse exponents, right? So with that being said, logarithmic functions are inverses of exponential functions, okay? So we learned a little bit about inverses in chapter 6 or unit 6. Inverse means that those two functions are reflections over the line y equals x. So for every logarithmic function, there is an inverse, okay? An inverse exponential one. So we learned that the asymptote for an exponential function is horizontal. So what do you think the asymptote of a logarithmic function is? Any guesses? Opposite of horizontal is?
Vertical.
Yes, good. Everything about these is backwards. So we learned that in an exponential function, the domain is all real numbers. So in a logarithmic, the range is all real numbers. In an exponential function, we learned that the range is asymptote driven. So the domain of a logarithmic function is asymptote driven, because with inverse functions, the x and the y are flipped, which means the domain and range are flipped as well. To find the vertical asymptote, you simply set whatever's inside these parentheses equal to 0 and solve for x. Okay? Now, how do you set up the parent table? Well, I came up with a more simple way for you to do it here. Basically, your y is always going to be 0, 1, and 2 for the parent. And then the other side of your table is going to be 1, b, and b squared. Now, what is b? b is going to be the base of your particular log. So let's go ahead and try it. It's easiest to see when you do an example, I think. So the very first thing you're going to do here is you're going to identify if there are any transformations. There may or may not be. In this particular case, with any function that we deal with, we have an a, an h, and a k. We all know what a, h, and k do by now, right? In general, a affects the reflection, vertical, compression, and stretch. H is left, right, and k is up, down. Remember that? So, do we have any transformations on this one? No transformation, and that's because I don't have an a, h, or k that are any number, okay? So what you're then going to do is you're going to write the parent function above this little table right here. And that's because the parent function is simply whatever your log is, log x of whatever your base is. So we don't have any transformations on this one, so the parent is the function itself, okay? Now we're going to identify the asymptote, and you do that by setting whatever this value is here equal to 0. So if I set x equal to 0, is there anything to solve there? No, so my asymptote is just x equals 0. Now the range for every single logarithmic function is always negative infinity to positive infinity. So every single person in here can get this question right on the test, okay? The range is always the same for these. As long as you pay attention, you can get that one. That one's an easy one. So here's how you set up your table. This is going to be, for your parent, 0, 1, and 2. And this is always going to be 1, your base, which is 5, and your base squared, which is 25. Now, if you're wondering, well, why? Where did those numbers come from? Let me explain. If I rewrite my log like this, I can use the arrow method to get it back in exponential form. That's going to be 5 to the y power is equal to x. If you take any of these sets of values and plug them in here, you're going to see that to be true, right? So we have 5 to the 0 power. Anything to the 0 power is 1. That's where the 1 came from. If I take 5 to the y, like we just said 1, what is 5 to the first power?
5.
That's where the x came from. If we do 5 to the second power, what is 5 to the second power?
5.
So that's where they come from, if you're wondering the reasoning behind that. But there's a rule that always applies, so you don't have to do that math every time. Now, if there were a transformation, you would apply the transformation. I'd write the transformation in these boxes and apply it. So h affects your x, so your x is affected by h, and your y is affected by both a and k. Now, luckily here we don't have any of those manipulations on our graph, so I can simply just copy over my table, because there are no transformations. It hasn't moved, okay? Now all we're going to do is we're going to plot these points. So I have 1, 0, I have 5, 1, and then of course I have a point that's certainly not going to fit on my graph. So what we're going to now do is we're going to graph the asymptote. X equals a number is always a vertical line that goes through that x value. The x value of 0 is right here, so the line x equals 0 is actually the same thing as the y-axis. So this is the vertical asymptote, x equals 0. Now, you don't know what these graphs look like yet, so I want to show you. Here's how you sketch them. It always has to hug your asymptote. Okay, and if you're wondering, you just follow the points. If the points are going downward toward the asymptote, you're going to go downward. If they're going upward to the asymptote, you're going to go upward, okay? So that's what it looks like. Now, how do we determine domain and behavior? Let's go ahead and address that. Domain is asymptote driven. Domain is what we do from the left to x to the right. Now, what is the most left that my graph ever goes on the x? 0. But 0 is not included because we never actually touch our asymptote. Yep. Plus, and we go to the plus side over here, then we're going all the way this way forever. Okay? Now let's talk about end behavior. So what the graph's doing here, and what the graph is doing over here. So, does my x ever approach negative infinity? The closest it gets to negative infinity is 0. As my x goes to 0, what is my function doing? Negative infinity. Over here on the right, does my graph go off to positive infinity?
Yep.
Yes. And as it does that, what is the f of x doing? The function's going slowly, but surely it's going up, which means it's going to
Positive infinity.
very good. So not so bad. All right, any questions about that? We're going to do a few more examples. All right, so we're going to look at 2 examples that have transformations on them. So, bless you. First thing you're going to do is you're going to identify the parent function. The parent function is always y equals log whatever your base is, which is 2, of just plain old x. Okay, don't worry about any of the transformations. That's your parent function, PF, parent function. Now we're going to describe the transformation that exists on my graph. I see here that I don't have any A to worry about, so I know I don't have a vertical stretch, compression, or reflection. But I do have this right here, which tells me I have a horizontal shift. Now, what do we know about horizontal shifts that's a little bit weird?
The negative is positive.
Yeah, so it's actually 2 units to the
Right.
right. But additionally, my graph is also going 3 up.
By 3.
Good. Now, reminder on how to find the asymptote. You simply set whatever's in these parentheses equal to 0 and solve for x. So that's going to solve to give me x equals 2, and that'll be the equation of your asymptote. The range is always negative infinity to positive infinity. Now we're going to set up our table, and I showed you the reasoning behind why these values come about, but so now that we know that, we can speed it along a little bit. We have 0, 1, and 2, and this is always going to be 1, your base. What's my base here?
2.
And my base squared is?
4.
Good. Now we're going to take this and apply the transformation. So as I said earlier, this is based on h. X is affected by h. And then y is affected by both a and k. The good news in this case is, do we have an a to worry about in this one?
No.
Just the k. So what you're going to do is you're going to figure out how that affects each of those values. The k is going 2 to the right. So if we're going 2 to the right, what's that going to do to each one of my x values? It's going to add 2 to each of them, right? And then we don't have an a, so what is the up 3 going to do to all my y's? It's going to add 3. Now say you had an a, we will do one with an example with an a. You know I always do every type of example. You would take the a, multiply your y by the a, and then add or subtract your k. And the way I tell you to remember that is a comes before k in the alphabet, so you apply that transformation first. So let's go ahead and try it. We're going to take each of these x values and add 2 to them. What's 1 plus 2?
3.
Good. 2 plus 2?
4.
And 4 plus 2?
5. 6.
6. Now we're going to take our y's and add 3 to them based on the k. So that's going to be 3,
4 and 5.
4, and 5. Now we're going to plot our actual graph. 3, 3, 4, 4, and 6, 5. Before we connect, we're going to plot our asymptote, which we determined to be at positive 2, right here. And then our graph always hugs the asymptote, gets really close to it, but doesn't quite touch it. Of course, ours is going to technically touch it. That's okay. All right, so now that we have it, we can go ahead and evaluate the rest of the information. My domain is going to be from my asymptote to positive infinity, because my graph starts here and goes over to the right. Now, end behavior. Does my graph ever approach negative infinity on the x? Does it ever always go, does it take on all these x's over here ever?
No.
No, because it never crosses the asymptote. So the closest it gets to that is 2. And as it goes to 2, my graph goes down to negative infinity. All right. In the yellow, my graph is going to the right, approaching positive infinity. And as it does that, my graph goes up to positive infinity. Okay. Everyone good with that? I think we've evaluated all the points. So now we're going to go ahead and try one that has all 4 types of transformations. So we're going to write our parent function. Parent is y equals log base, whatever your base is. Our base is 3 of x. Now we're going to describe the transformation. That negative sign tells me I have a reflection. That 2 tells me I have a vertical stretch of 2. That means it's stretched this way. Okay. That plus 3 tells me I go 3 to the left. And that minus 1 tells me I go 1 down. My range is always all real numbers. Now we're going to make our table for my parent function. It's always 0, 1, and 2. That only is for the parent function, not for the transformation, so don't mix those two up. This is always going to be 1, your base, and then your base squared, which is 9. Now here's the part that we want to be careful about. Before we do that, actually, what's my asymptote here? X equals negative 3. You set this equal to 0. Okay. So, I'm going to zoom in so you can see it better. Your x is k driven, and your y is based on a and k. So if we're going 3 units to the left, that means we're going to take each of our x's and subtract 3 from them. Okay, because left-right is controlled by x. But vertical stretch and vertical shift are controlled by what the y is doing, because they take up the vertical part of the axis. So for my a, we're going to take each of my coordinates and multiply them by negative 2, because that's what my a is. And then once we've then done that, we're going to apply the vertical shift. We're going to subtract 1 from them. So you always do a, then k. A, then k. A comes before k in the alphabet, so you'll never forget. Okay? So let's do that. So you're going to take these and subtract 3 from them. That's going to be negative 2, 0, and 6. Everybody see how I got those? Now we're going to take our y, we're going to multiply by negative 2, and then subtract 1. So 0 times negative 2 is 0. 0 minus 1 is negative 1. 1 times negative 2 is negative 2. Negative 2 minus 1 is negative 3. And then 2 times negative 2 is negative
4.
Negative 4 minus 1 is?
Negative 5.
Good. I just go through, I check my work, and now I can graph my function. So I have negative 2, negative 1, 0, negative 3, and then I have 6, negative 5. H, and then k. Multiply, subtract. Okay. So I'm going to graph my asymptote at -3, like that. And then I can follow the asymptote up with my graph. So it looks like this. And it makes sense, it's flipped around, like the other one's the other way, this one's reflected. So my domain, of course, is going to be -3 to positive infinity. Everybody see why that is? Okay. And behavior. What's the graph doing right here? Well, it's never going past -3 on the x, but as it goes there, what is the function doing up here? It's going
Increasing.
good, going up to positive infinity. Over here, as x goes to the positive infinity direction, what is the f of x? What is the function doing?
Going negative.
Going negative. Okay. Makes sense? Would you like me to show you how to do it on Desmos? Yes? Maybe?
Yeah.
Alright. I will show you, but I want you to make sure that you understand these graphs are not going to be as easy to work with in Desmos as other graphs, so sometimes it's actually easier to do by hand. So I will show you. So say I want to plot the first graph, y equals. So there's two ways to do it. You can type in the word log, and then you got to do that little subscript. So here's how you do the subscript on the keyboard. If you click the keyboard button on Desmos, there's a little ABC button. You click that. It's kind of hard to see with the red lines here. Let me show you. You see that? Of course. hang on. Do you see that button, A sub B right there? That will give you an option to do a subscript. I think you can also maybe hit the down key on your keyboard if you can. So you type the base, and then you can click out, and then you can do x minus 2, and then plus, what is it, 3? That's how you do it. But it's really hard to find nice coordinates because very few actually exist, so just be careful. And then of course you can do your table and all that fun stuff. And then you could also graph your asymptote. Now here's why these graphs are really strange. If you zoom in here, what's going to happen is it's going to get really, really close to the 2, and then it will go down forever on really close to the 2. Okay, it's not going to actually touch it, but it's going to look like it does because it gets super, super close. Okay, so yeah, that's all I have for you today.